All right, good morning, everyone. Today is Monday, November the 8th. We are on day 2 of 4.04. And on the screen here is the bell work question and the solution. All right, let's get into today's lesson. All right, graphing logarithms, the Logness monster. Now, the reason why it's called the Logness monster, well, it's because every log graph, assuming there's no like negative causing it to flip, but all log graphs without that transformation create this graph that looks like this. It just starts down here and goes up, and then as it kind of goes above the x-axis, it starts to drift to the right. So the Logness monster, log graphs. That's how all log graphs look. All right, make sure you got your paper, pencil, pen, graphing paper, if maybe you got it, Desmos, GeoGebra, be fine. All right. All right, so what is a logarithm? Well, logarithms are the inverse of exponents. So we did inverse equations last week in solving. Well, logarithms are the inverse of exponents. So the function y equals b to the x, the inverse of this function or this equation is x equals b to the y power. So remember last week, whenever you wanted to find the inverse, we would just switch x and y, and then we would resolve. So we switched x and y, but we didn't resolve it. So we do have to solve for y, but this is the inverse to start. And then you do the math, and the inverse, we get y equals log base b of x. So after we switched x and y, you solve for y and you get this. Well, we're kind of missing the steps, right? So the module shows finding the inverse of logs by using this little formula. So this is the formula to convert from this into this. They don't actually show the math that's involved. So there's where my live lessons, recorded lessons are going to differ from the modules. I really hate using formulas like they do in the module to show how to solve for, well, logs or natural logs. My approach of how I teach a mathematical approach that doesn't require memorizing this formula. So you can decide which way you like better, using the formula or actually using the math. All right, so let me show you that math. So again, here's the little conversion formula. When you have x equals a to the y power, the conversion to solve for y is, well, straight to this. So you get y equals log base a of x. So when I say log base a of x, this is not this piece times x. This is the entire number. It's like saying sine of x or cosine of x or tangent of x. Tan or sine or cosine, it's not a number. It's the sine of x is the entire number. Same thing with logs. Log base a of x is the number. So like we couldn't divide both sides by log base a. Similar to we couldn't divide both sides by sine, because sine of x is the number. I really hope that makes sense in using that analogy. All right. So let's do the math. And again, if like it says here, if you know how to do the math, you don't need to memorize the inverse form. All right, everyone ready? Guys, I really hope you're paying attention here because this is going to feel like doing math for the first time. You're going to learn new operations here. All right, so our goal is to get this y down from the exponent. So how we do that is we are going to log base b both sides. And we're doing log base b because the current base, this base b raised to the y power, this determines what our log base is going to be. So if that's a 5, we're going to make this a 5. We want these numbers to match, or in this case, these variables to match. So we are log base b both sides. This is similar to like if we were to square both sides or square root both sides. We are allowed to log base both sides. Good so far, everyone? All right, next. Now, a log property that we haven't ever learned before until just now is when you have log base b of b raised to some exponent, we are allowed to take this exponent and move it in front of the log. It is a log property that we can do that. So log base b of b raised to the y power, the exponent can move to become a coefficient. So now it's y times log base b of b. That is a log property, and we will talk more about that in the next coming days, along with today. And vice versa. If you have the coefficient y, so y times log base b of b, that coefficient or that scalar can move from the front back to the exponent. How cool is that? So cool. All right, next. Whenever you have log base b of b, whenever these numbers match, this is always going to be equal to 1. So if that was log base 5 of 5, it equals 1. If that was log base 10 of 10, it equals 1. So this piece becomes a 1. And 1 times y is just y. And then we're done. That's it. And we just rewrite it with y on the left side. So y equals log base b of x. How neat is that? And then we got right from this to this without memorizing a conversion formula. Way better. Way better. Well, it's weird, Brady. That's actually a good descriptor. It is weird because, well, you're learning a new operator. Like when we first started doing math, we learned addition, subtraction, multiplication, then there's division. And then you learned you could square both sides, and you learned you could square root both sides, and it was like, wow, this is all weird. Well, now you learn that you can log both sides or natural log both sides. Yeah, once you see numbers, it'll be better. Yeah, seeing like solving equations with just variables for whatever reason is weird. It's just hard for a lot of people. I get it. All right, now let's go the other direction. So once we're here, now let's go back to see that we can actually do math to get back to, well, the original. All right, you ready to have your minds blown right now? Now we learned that we can add both sides, we can subtract both sides, multiply, divide both sides, we can square both sides, we can square root both sides, we could log both sides. Well, guess what? We can base both sides. You're like, what? So remember, our goal here is, well, to get back to what we started with, right? This. So I want to get this x by itself. And to do that, I am going to base both sides with, well, this base. So log base b, that means I'm going to do a base of b to both sides. So now we have b to the y power equals b to the log of base b of x. Crazy, right? All right, so this is another log property. Everyone pay attention, another log property. When you have some base, in this case b, raised to, so this is in the exponent, so we have b to this power, so base b of log base b. So when these bases match, this b and this b match, this cancels out. So this cancels out, And then whatever the log is of, so log base b of x, whatever this is carries down as just an x. That is another log property that we got. So again, b raised to the log base b of x, since these match, they cancel out. And whatever your log is of, so log base b of x, this x carries down. And then we, of course, still have b to the y power. And look, now we're back to what we started with. How cool is that? X equals b to the y power. So no need to memorize formulas. Now, can you give me an example of real life scenario? So you mean like real life meaning numbers, right? With actual numbers. Sure. Yeah, I can do that. Like this one, right, Brady? Oh, wait, in life? Oh, like in real life? Well, we have a test next week. That's real life. You have a final in December. That's real life. Yeah, that's about sums it up. Oh, outside of school. Yeah, you'll never use it in real life. Yeah, but grades are real life. So in the immediate future. So why are we learning it? Well, it's because this class satisfies the university requirement, and people taking this class either want a challenge or they plan on going to a university right out of high school and not a community college. So you chose pre-calc instead of consumer math. Consumer math would have been real life. You'll discover in pre-calc most of the stuff that we do, you won't ever, like, you won't need it to be successful in life. You won't need it to balance your checkbook or to buy a car or buy a house. Yeah, so now trig on the other hand, trig can be used in real life, but the stuff that we do in trig is going to be like way beyond what is probably needed to do projects or whatever. Why did I choose a class I won't use again? Well, you chose pre-calc again because you wanted to go to a university right out of high school, and you wanted a challenge, maybe. Yeah, thanks, Enzo. Yeah, that might be a mostly true statement. This is true, Brady. Surprise! You all got lucky by having me as your pre-calc teacher. I know all of you are so thrilled. Can barely contain yourselves. Anyway, all right, let's do this problem here. Now, real quick, I wanted to point out, whenever you are logging both sides, make sure this term is by itself. Like if you have stuff outside, like plus or minus something else, basically, if you have more than one term, you have to get this piece by itself. Same thing over here. Before you base both sides, whatever you're trying to kind of free from the log, make sure that term, which is log base b of x, is by itself. So with that said, looking at this, we have y equals 10 to the x minus 9 and minus 4. We want to find the inverse. What is our first step that we learned last week? What is our first step? Before that, switch x and y. Yeah. So to find the inverse, you first have to rewrite it by switching x and y. So let's go ahead and do that. So on your paper, let's rewrite it as x equals 10 to the y minus 9 power and then minus 4. Okay, so I rewrote it with x and y switched. Now what do I do? Yeah, then add 4. So let's go ahead and do that. So we're going to have x minus 4 equals 10 to the y minus 9. All right, now what? Remember, our goal is to get this y by itself, and right now it's kind of stuck in the exponent. No, if you do a root of y minus 9, can you imagine a radical symbol with the y minus 9 as the index? Doesn't that sound like super awful? I did. Oh wait, did I not? Did my math? Because I was testing all of you to see if you would see that my pen ran out of ink in that moment. All right, we are going to log base. Yeah, log base 10 both sides. Absolutely. We're going to log base 10 both sides. Log base 10 both sides. Now you can see why I left a little bit of space there. And then don't forget, we are logging this entire left side. So what else do I need over here? Yeah, we need parentheses. Absolutely. Right now, what I have written there is log base 10 of x and not log base 10 of x plus 4. So you really have to remember to put parentheses. It does matter. It does. They are very different with and without parentheses. Now we're actually logging the entire quantity and not just x. All right. All right, what's next? Yeah, so the log base 10 of 10, it does cancel out because it becomes a what? Log base 10 of 10 becomes what? Becomes 1, yeah. But before we do that, what should we do with the y minus 9 exponent? It's one of the log properties. So if you're thinking of it, just log base 10 of 10 becomes 1, and then that exponent just carries down, you wouldn't be wrong. But yeah, we're going to have to carry it in front. Going to have to carry it in front. But it basically has the same meaning if you were to just cancel log base 10 of 10 and then the y minus 9 carries down. It'd be the same thing, right? So y minus 9 times log base 10 of 10. And then on the left side, and then a lot of you said that log base 10 of 10 becomes 1, and you are correct. All right, so now we have the log of all that stuff equals y minus 9. What should we do? Remember, we're trying to solve for y here. Yeah, add 9 to both sides. So when you add 9 to both sides, we just get y on the right side, and then we get, leave some room here. We're going to get, whoa, what is, thank you, Neuro. So log base 10 of x plus 4. And then we added 9 to both sides. And that's it. I also wanted to show something else. So when you have the square root Do those mean the same thing? Yeah, so if that index of 2 is invisible, we know it's a 2. Same thing that goes with log. So when you just have log and it doesn't have a base that we can see, it is always a log base 10. Just want to make sure you all know this. So whenever you see log without a base, it is an invisible 10. You need to know that. So like my answer that I have under here wrote the answer without showing that base of 10. All right, so let me show you something in Desmos. Let me just share my screen. Let's go Firefox. Why is it so slow? Okay, here it goes. All right, let me share my screen here. All right, yeah, what is... All right, everyone should see my Firefox. All right, I'm gonna go to Desmos. And then let's type in the original function. So y equals, what was it, 10, oops, 10 raised to the, I think, was it x minus 9? And then minus 4. I think that's right. Let me make it a little darker. There we go. Okay. So that was the original function. Now we do know that our graph should be reflected over the y equals x line. Right. So remember last week we learned that inverses are always reflected over the y equals x. And let me change that into a dashed line. Okay, there we go. All right, now the inverse that we found was y equals, what was it, log of, is it x plus 4 and then plus 9? Is that what it was? I think that's right. Yeah, that's right. And we can see that this graph is, here's the original, and then if we reflect it over the y equals x imaginary line, it creates, well, the reflection. So based on what we our answer was, and we graphed it, we can confirm that they are indeed reflections of each other, and it is correct. Let me see. I think, so let me hide this. And I think you have to bring up like the calculator here, calculator, and then where is, oh yeah, functions. And then we can do miscellaneous. And then, so if you notice, we have this log base A. So if I can click this, and now I can enter the base being a 10. And then I'm going to go, oops, should probably put y equals first. Y equals plus 4, and then plus 9. And then look, so yeah, it's the same thing. So this way I was able to actually enter the base of 10. So again, let me show that again if you missed it. So on my new line here, I click, well, I would do y equals first. Y equals, click the little keyboard icon. It brings this up, and then you have functions, click functions, and then you have all these choices. Click miscellaneous, and then you'll see log base A. You'll click that, and then you can enter the base if it's anything other than a 10. Okay. All right. All right. Let's try another one. All right, let's do this one together. All right, what's our first step? Before we remember, yeah, we have to switch x and y. So guys, always make sure when you find the inverse, you always switch x and y first. Okay, so once we switch x and y, now what do we do? And you could do it in the same step. That's probably fine. So yeah, add 9 to both sides. Now what? We're going to log base 3 both sides. Good. And it's based off of this. So if our last problem was a 10, so we log base 10. Now this is a 3, so we log base 3. And again, we can only do this step, logging both sides, once you have this term by itself. Because remember, our goal here is to free this y from the exponent. And to do that, this needs to be by itself on one side. Don't forget your parentheses around the x plus 9. It does matter. It is very different without the parentheses. Very different. Okay, then what? Can we just keep it this simple? No, that'd be too easy. That'd be boring. Yeah, y plus 1 goes in front. Yep. All right, what's next? The log base 3 of 3 becomes 1. Perfect. Yep, this becomes a 1. And then the y plus 1 just carries down. And I didn't write it last time, but I'll write it this time just to show that. Because 1 times anything is itself. And then don't forget our log base 3 of x plus 9. All right, now what? And subtract 1. Yep, and then we'll be done. And let's see if we're correct. And we are. Y equals log base 3 of x plus 9 and then minus 1. Perfect. Not too bad, right? Not too bad. Just learning these new operations, right? This part is not bad. Well, it doesn't get worse, probably. All right, let's go the other direction. So now we want to find the inverse of this log equation. All right, what's our first step? Ready? You're ready. Yeah, we switch x and y. So we get x equals is 5. Oops. All right, so now what do we do? Then add 10 to both sides. Very good. So we're gonna x minus 10. Remember, our goal, remember, we're trying to free the y from the log. So we need to get that log term by itself. And that's why we add the 10 to both sides to do that. I'm going to leave some space because our next step, we're going to have to do something, which you can probably figure out what it is. All right. What do we do? Yeah, so we want to base 5 both sides. And we're doing base 5. It's always is dependent on what this is. Well, that's a 5, so we want to base 5 because 5 raised to the log base 5, they're going to cancel out, and then this stuff just, well, carries down. So let me do that in green. We are going to base 5. So we got 5 raised to x plus 10 and 5 raised to all that stuff. So that means that log, so 5 raised to the log base 5, those cancel out, and then the y minus 6 carries down. All right, now what? Now we add 6. Yep. And that's it. We solve for y. We're done. Easy peasy. And that is correct. Y equals 5 to the x plus 10 plus 6. So again, make sure that after you switch them, to get rid of the log that's attached to it, we have to get this term by itself by adding 10, in this case, both sides. And then we can do base of 5 to both sides. That cancels out. This carries down. We have 5 to the x plus 10, and then, yeah, we're done. All right, everyone try this one. Give me a green check when you finish this problem. All right, what is the answer to this one? Oh, above. So y equals 6 to the x minus 10 power and then plus 4. That is correct. Nice job. Any of you want to see this worked out? Anybody? Well, I'll do a polling in case nobody wants to speak up. Choose choice D as in dog if you want to see it worked out. That way it's anonymous. Choose anything else if you don't. Okay, yeah, nobody wants to see it worked out. We're good. Good. Okay, let's go on. Okay, here are 5 more examples. I encourage all of you to work all these out of going from the log equation back to the inverse, which is gives us the exponential equation, and vice versa. So we can go from this way to this way, and from this way back to this way. So feel free to do that as extra practice along with the module. So even though the module doesn't approach these problems the same way that I am, by actually doing math, they do it using the formula. You can still work those problems out and make sure that you get the same answer they do. You need to do that at least. Okay, now the graphing part. All right, we got plenty of time. So the Logness monster, it creates this graph. We saw that on the graph we did in Desmos beginning of class. This is showing 2 different functions. We have f of x equals log base 3 of x, and then this gray line is g of x equals log base 6 of x. So looking at both of these equations and the graph, what is true regardless of the base of log? What is true? So what is true regardless of the base of the log? What do you notice? So look at this graph here. What's going on here? And then look at the equations. What do you notice? Yeah, they both move in the positive direction. Sure, they both have that that classic like fin look. Yeah, but what else? So ignore the whole like compression stretch aspect of it. Like what's true about both graphs? What is true? So Enzo's on the right track. Yeah, they share the same points. And what is significant or important about that point? It crosses at 1, 0. And what is 1, 0? Like, what's another name for that that point? Yeah, it's the x-intercept. So regardless of the base of the log, the x-intercept is still the same, which is at 1, 0. That is always true. So the parent function, meaning the original function that doesn't have any shifting, so no horizontal shifts, no vertical shift, the x-intercept will always be 1, 0. You need to write that down. That's important. Next, another important point on each graph. We are going to have something comma 1 and something comma 1. All right. The x value will always be the base. Will always be the base. So that means that first graph will always cross the point 3, 1. The second equation will cross at 6, 1. All based on the base. And we can see that for the blue function, f of x, 3, 1, it's this point right here. And then if we could see the rest of the graph, we would see that this gray one, this g of x function, will hit the point at 6, 1. And you can kind of see based on that path, 6, 1 is somewhere over here. So that is important to know. So two things. The parent function will always cross at 1 comma 0, so the x-intercept 1 comma 0. And then the other important point on your graph will always cross at the y value being 1 and the x value being whatever the base is of that log. So that's why this one hits at 3 comma 1 and this graph crosses or hits the point at 6 comma 1. All right, everyone's good? Enzo is stating truths. Yep. All graphs cross at b comma 1, and I actually do have that in the guided notes. It's just in a few slides here. Let me go to it and show you. Yes. So b comma 1. So this is kind of just stating. This should say the asymptote is parallel along the y-axis. It's not actually on the y-axis. Little typo here. X-intercept is always at 1, so 1 comma 0, and then another important point, like Enzo said in chat, is at b comma 1, and b being the base of your log. But going back to this, so we're going to use that. All right, so we are always going to, so the inverse, which is the blue graph, it's going to cross at 1 comma 0. That's the first given point, 1 comma 0, which is right here. And then the other point is going to be at the base of the log comma 1, and the base being a 2. And we can see that on the graph. 2 comma 1 is right here. So that's true. So when you're graphing these logs, you want to at least plot those 2 points. And we can see that here's the original, here's the inverse. This is the reflection line, y equals x, right? And this function is reflected over this like a mirror to create this. And we did that in Desmos with that first problem of the day after bell work. All right, same thing. All right, back to this page here. We already talked about these three. So log base 5 of 5, we also did talk about that. Remember when the base, so log base 5 of 5, log base 8 of 8, what does that equal? What do all those equal? Yeah, all those equal 1, and we talked about that already. Yeah, they're all equal to 1. Another way to look at this that I haven't talked about, and I probably will later this week, 5 to the first power equals 5. 8 to the first power equals 8. 10 to the first power equals 10. Let me do another little example, kind of give you a little preview later this week. But when I have, let's say, log, let's say base 2, let's do log base 2 of 8. Well, to make that true, it has to be 3. So log base 2 of 8 actually equals 3. If you were to type this in your calculator, log base 2 of 8, hit enter, it would give you 3 as the answer. And that's because 2 to the third power equals 8. And again, we're going to talk about more of that later this week, okay? All right, so graphing, now we have shifting rules. So those 2 points are all based on the parent function, a graph without any shifting, but really simple to pull out our shifts. It's same as conic, same as what we did last week. You have your h and k, h being your horizontal, k being your vertical, and this is always opposite, so x minus h, and this is always what you see. So what is the shifting for this? What's the horizontal shift for this log equation? 5 to the left is correct. So this one is left 5. And then what is the vertical shifting for this log equation? It is, in fact, down 4. Yep. All right, now my 2 points. So remember, the parent function of a log will always cross at 1, 0. That is always true. And then the other point that will always be true is it's going to cross at the base, 1. And what is the base of this log? The base is a 6. Yep. So I'm just going to plot those 2 points in green. So 1, 0, and then 6, 1. So there's the parent function. Theirs will be the 2 points, and then I would just draw a line through it. But because of shifting, I have to shift those points left 5 and down 4. So in the x direction, we are going left 5 for both points, and then the y direction, we are going down 4. So subtract 4 from the y value. So 1 minus 5, I'll go back to blue color. So 1 minus 5 is -4. And then 0 minus 4 is -4. So there's my first point. And then my other point that I had to shift, 6 minus 5 is 1. And then 1 minus 4 is -3. And we can see if those are true. So again, from this point, I would just go left 4 units. Sorry, left 5 units, not 4. Left 5 units. And then I go down 4. 1, 2, 3, 4. So there's my first coordinate, -4, -4, which is correct. And then for this other point, we're going, again, shifting left 5 and down 4. So left 5 and then down 4 gets me right here. Let's go ahead and plot those 2 points again. So there's that first point, and then here is the other point by just applying those shifting rules. And then once you have those points, we just best we can. I guess that's good enough, right? And then I would erase my original green points because that's the parent function without shifting. Not too bad, right? Not too bad at all. As long as you understand the original 2 points. Yeah, not bad at all. And that's all you need is really 2 points, and you just rough sketch. And we can always go to Desmos and type this in to verify that these points are correct. Another good way to check. All right, everyone, let's do number 2. We're gonna skip number 1 for right now. Everyone do number 2, and then give me a green check when you are done with it. right, what are those? What are the two new points that you found? Two comma -5 and 5 -4. 2 -5. So right here and 5 -4. Yeah, I think, let's see. So we got 1 comma 0 and then 4 comma 1. And you said, so that means you are shifting to the right 1 and then you are shifting down 5. So we're adding 1 to the x. And then we are subtracting 5 to the y value. Yeah, so that looks right. 2 comma -5 and 5 comma -4. Yeah, it looks good. I do got to show one more thing before you guys take off. Is this page, these next two pages. So we learned last week about the domain and range of your exponential growth or decay problem, and it's all based off the vertical shift. So domain is all real numbers. The range is based off of your vertical shift. In this case, it's +0. That's why it's from 0 to infinity. That's from last week. So when you find the inverse of y equals b dx, which we now know it's y equals log base b of x, what do we do with domain and range? You know, if we know the domain and range of the original, what's the domain and range of the inverse? Yeah, they just flip. They just flip. So all real numbers becomes the range, and then 0 infinity becomes the domain. So that's from last week. Nothing different. And then I do have 2 more problems, but we can skip these. Feel free to work them out. And guys, make sure you go through the modules and work out the examples and compare what you get with what the those modules have for their answers as practice. Remember, that is your practice. That is your homework every single time. All right, everyone. Well, thanks for coming, and I hope you learned something. I will see all of you tomorrow for day 3 of 4.04. All right, everyone, have a great rest of your Monday.